In database design, large relations or tables can suffer from redundancy and unwanted dependencies. This leads to problems called anomalies, such as insertion, update, and deletion issues. To address these issues, we use decomposition, which means splitting the large relation into smaller, more manageable ones. This improves data consistency and simplifies maintenance. However, improper decomposition can cause data loss or broken dependencies. Therefore, it's crucial to understand the desirable properties that make a decomposition good. Decomposition involves breaking down a large relation into smaller subrelations, each containing meaningful subsets of attributes. The goal is that these smaller relations, when combined, accurately represent the original relation without any loss of information or introduction of inconsistencies. This process is a fundamental part of database normalization, aiming for efficient data organization. A well-designed decomposition should satisfy three key properties: lossless, non-loss decomposition, dependency preservation, and minimization of redundancy. These properties ensure the database remains consistent, efficient, and anomaly-free. Achieving all three simultaneously isn't always possible, and sometimes trade-offs are necessary, especially when aiming for higher normal forms like Boyce-Codd normal form, BCNF. Lossless decomposition means that when you join the decomposed relations back together, you get the original relation exactly. No data is lost or extra data added. Formally, for a relation R decomposed into R1 and R2, the natural join of R1 and R2, denoted as R1 join R2, should equal R. This is vital for data integrity, preventing incomplete queries or erroneous joins. The key condition is that the common attribute, or join key, must be a superkey in at least one of the subrelations. Here's an example showing a relation R being decomposed into R1 and R2, then recovered through natural join to get back the original R. This image illustrates the natural join operation, where relations R and S are joined on their common columns to produce a combined result. Finally, this tree diagram shows how a relation can be decomposed into multiple subrelations in a hierarchical manner. Consider a student relation with attributes role-no, name, course, and course fee. We have functional dependencies. Role-no determines name and course determines course fee. If we decompose this into R1 containing role-no and name, and R2 containing role-no, course, and course fee, the decomposition is lossless. Joining R1 and R2 on role-no will perfectly reconstruct the original student relation because role-no is a key in R1. Dependency preservation ensures that all functional dependencies from the original relation are either preserved directly in the decomposed relations or can be derived from them. This means no functional dependency is lost during the decomposition process. Preserving dependencies ensures business rules and constraints remain enforceable without requiring complex joins, reducing query overhead, and maintaining referential integrity. Here's an example of dependency diagrams showing how functional dependencies are represented visually. And this shows the closure of functional dependencies, demonstrating how dependencies can be derived. Suppose the original functional dependencies are role-no determines name and course determines course fee. We decompose the relation into two smaller relations, R1 containing role-no, name, and course, and R2 containing course and course fee. The functional dependencies are split between the two relations but fully preserved. R1 maintains the dependency role-no to name and course, while R2 maintains the dependency course to course fee. This means all original dependencies remain enforceable within the decomposed structure without any loss. Decomposition should eliminate or minimize duplicate data across rows, ensuring each fact is stored only once. This reduces storage costs, prevents update anomalies where changes require updating multiple rows, and improves query speed. Attributes with repeating values, often due to transitive dependencies, should be isolated into separate relations. Consider the employee table with redundancy in department information. The table shows EMP-ID, EMP-name, DEPT-ID, and DEP-name, where DEP-name repeats for each employee in the same department. The relation employee with EMP-ID, EMP-name, DEPT-ID, and DEP-name has functional dependencies where EMP-ID determines EMP-name and DEPT-ID, and DEPT-ID determines DEP-name. Decomposing into R1 and R2 stores DEP-name once per department, not per employee, reducing redundancy. This isolation of repeating attributes, often caused by transitive dependencies, ensures efficient storage and maintenance. By decomposing, dept name is stored once per department instead of repeating for each employee, effectively minimizing data redundancy.